Good morning.
Good morning, Dr. Wayne.
Good morning.
Good morning.
Good morning. Good morning. Okay, good morning, everyone.
Good morning.
Okay, so any questions regarding the class, the labs, lectures? All right, so just a reminder. So today you will turn in the practice question for chapter 19. So you turn in by go to Canvas, take that quiz. Right, so we will study the chapter 20 electrochemistry. So we will start with this practice exercise. So in this question, we are given two half reactions in a voltaic cell. So they are zinc zinc solid produce zinc 2 plus equals ion plus 2 electron. The electrode used, which means those solid material, metals or graphite. So in this electrode, we use zinc. In the other half reaction, so we have this chloride aqueous plus 6 H plus aqueous plus 6 electron produce chloride aqueous, then 3 H2O liquid. So the electrode on this part, we use Pt, which means platinum is one metal. So in the first half reaction, and we use the zinc metal because zinc is in the chemical reaction, so we don't have to use other metals. The second half reaction, you can see in the equation all the materials or all the substance ions in the equation, they are not solid, not metal. So we need some kind of carrier to carry the electrons. So usually you will choose some of those metal not involved in these reactions. So the metal may be platinum, maybe some other like nickel, some of those relatively inert metals, or you can use a graphite. All right, so therefore we can make it our voltaic cell. So then this question is, you want to indicate which reaction happens at the anode and which reaction happened at the cathode. So by definition, the reaction occurs at the anode as oxidation. So at anode, you will see the oxidation reaction. So oxidation and the reductions happens together, but we can think of oxidation is one half reaction, and the reduction is the other half reaction. So actually, they are just both two reactions, but they cannot happen by themselves. So they must happen together. Okay, so once we know our convention or definition, so that's definition. So what do we mean by anode? What do we mean by cathode? The definition is at the anode, you will have the oxidation. At the cathode, you have the reduction. Then you can use quite a few different ways to see what reaction is oxidation, what reaction is reduction. So one common or earlier way to see oxidation means loss electrons, and reduction means gain electrons. So by knowing this definition, so what is oxidation, what is reduction? Let's look back into these two reactions. So in the first reaction, so zinc solid becomes zinc 2 plus ion, then produce 2 electrons. That means zinc in this process, zinc solid lost 2 electrons. Okay? So therefore, zinc has been oxidized. So therefore, this half reaction is oxidation. And then we know oxidation at the so-called anode. All right, so then we can see this second half reaction. You can see one easy way to see this is the reduction by say this reactant, which means plus 6 electrons. So in the reduction reaction, the electron is a reactant. So that you can see in details who has been reduced. You just, in this example, you probably cannot see clearly the electron, so you can use oxidation number. Okay. So you can see ClO3 one negative, and in this ClO3 one negative, we use a rule. We say this oxygen has oxidation number -2, so therefore this chlorine is plus 5. Why? Because 5 then plus 3 times -2 equals -1. All right. So the second half reaction, just say you have ClO3 one negative, then plus 6H plus, then plus 6 electron. So you want to see who has been reduced. So on this side, so clearly this chloride ion -1. And then you can see here this 3H2O liquid. So this H is still +1 and oxygen is -2. So therefore, what has been really reduced is Cl. So we know that because the Cl chlorine's oxidation number changed from +5 to -1. So we know if the oxidation number decreases, so the element has been reduced. Therefore, this reaction is our reduction reaction, and this is at our cathode. All right, any questions regarding this first part of this problem? Okay, question? Okay, so then I will erase those on the screen, and we'll see the second part of the question. Okay, so sorry. I just show you on the assignment. So you can get the free Microsoft Office from your ASU email account. So I just get this new version of the Microsoft Office PowerPoint, which is 2016, and it's very good. Have some more features. So the second part of the question is, does the zinc electrode gain, loss, or retain the same mass as the reaction proceeds? So zinc electrode, this is zinc electrode, and this is on the anode. So you can see from this reaction, as reaction goes on, so this zinc here is our reactant and also a metal, so it's an electrode. So obviously, the zinc solid dissolve. So therefore, what happened to the mass? It will lose the mass. Okay, so the question C is, does the platinum electrode gain, loss, or retain the same mass as the reaction proceeds? So this, regarding this electrode PT, you can see PT just as an electron carrier. It did not participate in the chemical reaction. Okay. So PT not participate in this chemical reaction, so therefore it retains the same mass. Okay, so then which electrode is positive? So in a voltaic cell, so this positive negative depend on what kind of cell. Voltaic cell means the cell to produce current or electricity. So in this voltaic cell, the cathode is positive. So then who is a cathode? So cathode is PT in this example. All right, so those are the fundamental basic definitions for a voltaic cell. Okay, so then how do we quantify what happens, how much cell potentials, how much driving force? We use this so-called electromotive force. Abbreviation you will see a lot from here on, EMF. So imagine an analog. So we can see this waterfall. The waterfall from a higher potential energy on the top of the cliff to a lower potential energy spontaneously. And so similarly, we can compare electrons. Electron will flow from a higher potential. Usually that will be on the anode. On the anode, you will have some of those more active metal. So when the metal are more negative, they lose electron easier. And that's the driving force. That's the potential. So therefore, we will use some of those tabulated data to compare how easy the something being oxidized, or how eager something want to be reduced. So few few years ago, or maybe 20 or 30, 40 years ago, scientists use the oxidation potential to see who is more easily being oxidized. So now in these days, we are using the reduction potential. So we will see the table, give you those numbers. Those numbers tell you what are the possibility or the potential for something being reduced. So therefore, we'll call them those electromotive forces. So once we know the electromotive forces for the anode cathode, we can use a simple formula to calculate the cell potential. So those potentials, we measure them in watts. The cell potential or the EMF, we measure them in watts. So the definition is 1 watts. So 1 way is 1 J over 1 C. So C is for Coulomb. All right. So the reductive potential for is the common way we are using in these modern days. Reductive potentials for many electrodes has been measured and tabulated. So the values are compared to the reduction of hydrogen as a standard. What that means is we don't know like absolutely how much reduction potential for a metal, for example, for zinc. So what is the magnitude or the potential for zinc being reduced? Or zinc 2 plus ion being reduced. We don't know exactly that number, so we have to choose a reference. So the usual reference is using hydrogen as a standard. So using the H plus as a standard. So H plus can also be reduced to, we can think about 2H plus 2 electrons produce H2 gas. So this is our standard. So this is aqueous. Because we know like a reduction reaction always happen in pairs. So you want to know like what is the potential for zinc to be reduced. So you can think of zinc aqueous then plus 2 electrons to become zinc solid. So compare these two and see what are the potential. So you have to choose a reference. So you choose that H as the standard, which means you choose that as 0. And so the chemical reaction happens depend on the conditions. So the so-called standard condition is concentration. So this is concentration. For those something in solutions, and this is the pressure, and this is temperature. So we specify what do we mean by standard condition. So that's the specification for the standard condition. Okay, so once we have this concept, you can see this table. On this side, you see this number here is E naught, which means standard. When you see that little 0 something or O something on the top, which means a standard condition. So this red means reduction. Okay, so way means what? Okay, so this The modern table just give you those numbers for those guys being reduced. So you can see here, the first one is a fluorine. So fluorine here as reactant is element. So the oxidation number for fluorine in element is 0. And here the -1. So your oxidation number decreases, so we know fluorine has been reduced. Okay. So all those reaction here, those half reaction, is written as half reaction. So this half reduction reaction. All right. So those reaction right on the top of the table. So they have a higher number or more positive number of this reduction potential. That means they are more eager to be reduced. Or you can think about the other way. So those species here are stronger oxidizing agents. So those top species are stronger oxidant. Oxidant means oxidizing agent. Okay, so more data. And you can see in this table, we see our reference. So our reference is this. So we usually call that SHE. So that means S means standard. H means hydrogen. E means electrode. So that's SHE. If you need more those reduction potentials, you can go to Appendix E in the textbook. And this what the SHE looks like. So you can see here the so-called SHE. SHE. Okay. So technically, any of those half reaction on the table, so those half reaction on the table, okay, they are written as reduction reactions, but obviously you can reverse them depending on who you pair them up with. So similar for this SHE, it can be used as a cathode, it can be used as anode. Okay, so the reference is called, so our reference, we call our reference the standard hydrogen electrode. By definition, as the standard, the reduction potential for the SHE, so here means SHE is 0 volts. And so structurally, so what SHE looks like, it looks like you have a little reservoir of solution. The solution should be acidic, so the H plus is 1 molar. And then you have this little tube. Then you will put those H2 gas. The pressure should be 1 atm. But everything here is not solid. You have to choose electrodes. You can choose graphite or platinum, or you can use silver or gold. So we use a platinum. So the hydrogen gas will come in and bubbles out. And then you connecting this to the other electrode. Okay, so depending on the other electrodes, so this SHE can be a cathode, can be an anode. So if this is cathode, which means H plus has been reduced, so the half reaction will be 2 H plus after as you want to specify the state, specify the concentration, and plus 2 electron become H2, which is the gas. The pressure should be 1 atm. when the SH is the anode, that means hydrogen has been oxidized. So you will reverse the way you write the equation. So you will write 82 gas 1 atm plus 2H plus aqueous 1 molar plus 2 electrons. So that's our reference. Right. Any questions? Okay. So then once we know those reduction potential of the electrode, so those half reactions, the half reaction together give us the overall reactions. So the cell means from over, I will usually call them overall reactions. Overall reaction equals the oxidation reaction plus the reduction reaction. We can call that total. So overall or the total. So this is a half. This is a half. So half plus half is total. So you want to calculate what is the so-called cell potential for the overall reaction. You use this formula. So that means you identify what is your reduction reaction. So reduction reaction will be on the cathode. So this will be our reduction reaction. On the anode, so be our oxidation reaction. And then just go to the table to find out the number. So this is easy because what you see is exactly on the table. So the way you write the equation for the cathode reduction reaction, easy because it's exactly appears as written on the table. What table? Table means those standard reduction potential. So the oxidation is a little difficult because oxidation is written oppositely as in table. Okay, so all those reactions written in the table are reduction. If you identify your oxidation, so obviously your oxidation will be the opposite way as written in the table. Okay, so because cell potential is based on the potential energy per unit of charge, so therefore it is an intensive property. So that means does not depend on how you write the equation. If you multiply the equation by some numbers, your E cell stays the same. All right. So here is one example of a cell. So in this is our example of Wojciech, which is named after Watani, which is an Italian scientist about 400 years ago. So he first discovered the muscle in frog legs has electricity. For this chemical reaction, we can see our anode is this zinc electrode. So zinc lost electron being oxidized. So those lost electrons flow out from the external wire to the copper electrode. So once the electrons accumulate on this copper electrode, electron negative, so the plus ion plus CO2 plus ion be attracted to the electrons, so therefore this reaction happens. So copper 2 plus 2 electron become copper solid. So we can see our two reactions. So this is a reduction reaction. This oxidation reaction. So as I said, this equation exactly matching what you will see for copper plus 2 plus ion in the table. But this one is written the reverse way. So then don't worry, just know you have this reaction happen on the anode. Just looking the reverse way in the table, find the number. So you will find a number. So for this number means you will have this zinc from the table written will be zinc 2 plus ion aqueous plus 2 electrons produce zinc solid. So obviously this equation written here did not really happen in this cell. In this cell, this reaction happened oppositely. But we'll use this number for our anode. And also don't confuse by this guy. So this means reduction. So even though we know on the anode we also have the oxidation, but we'll use this reaction's reduction potential to calculate our cell potentials. So then we identify our cathodes. So that will exactly this reaction happens. So like Cu2 plus aqueous plus 2 electron produce Cu solid. So that we know we have this half reaction. We have this number E naught reduction with positive 0.37 volts. Okay, so once we know this carbon numbers, and then what we do just to use our formula to do the calculations. So your calculation will be E cell equals E cathode minus E anode, and then you just part of those numbers. Your E, so this number cathode is this number. So 0.37 volts or positive 0.37 volts. So we plug in the minus from this minus, and then this number will be this number. So therefore minus negative 0.76 volts. So obviously you take these two numbers multiply, or you take the number like subtracting negative means plus, you get 1.10 volts. So that's how you calculate this guy. So far, we know this not means standard, and then later on we'll learn the way to calculate those cell potential that's not a standard. Okay, so this question is using the data in table 20.1. What value will you calculate for the standard EMF, the so-called E cell, for voltaic cell that employs the overall cell reaction, so this overall cell reaction, and so then you identify in this overall cell reaction, that is very, very important. So if I give you this overall cell reaction, you have to identify what is your reduction. So what is your oxidation? So reduction means it happened on the cathode. Oxidation happened on the anode. Okay, and then you can see in this reaction on the top, and you circle this on top of overall, we have Ag plus aqueous nickel solid produce Ag solid nickel aqueous. So this kind of relatively easy. We can see we have a silver ion become silver solid. So therefore, silver has been reduced. So therefore, we write our reduction reaction. So Ag plus aqueous. Well, you can, if you take that from the overall reaction, for use 2 Ag plus 2 electron produce 2 Ag solid. So that's our cathode reaction. Our anode reaction, so just other parts left over, which means nickel solid becomes nickel 2 plus ion in aqueous plus 2 electrons. All right. So then our formula to calculate that E naught cell or equals E naught red means reduction. Then you will see the cathode minus E naught reduction, and then the anode. Okay. So what you see is so this number here is just a notation. So then matching what you see from the table. Right. So then we know on the cathode is this reaction. So therefore we just use this number as written in this reaction, exactly as what I write. So 0.8080 watts. Then minus from the formula. The problem is sometimes you get confused is, you see on the anode, I have this reaction. On the anode, I have nickel solid produce nickel ion. But the table gives me nickel 2 plus ion produce nickel solid. So what should I do? Should I reverse the reaction or should I reverse the sign? So some books do that, then you will have a different number for here, a different sign for here, for this guy. But this book is written as minus this E reduction of anode. So what you do, you just keep this reaction, keep this number as it is. So you're matching this oppositely. So therefore, you just see minus negative 0.28 watts. Okay, so therefore that become 0.80 watts plus 0.28 watts equals 1.08 watts. So that's our way to calculate the standard E0 cell. Therefore, our answer is C.
Doctor,
Yeah, question?
certain people still have on their mic and it's kind of distracting. Can you mute all? Is that possible?
Okay. Let me see.
Thank you.
Welcome, Christina. Okay, so how do I mute every? Okay. Okay, you can still hear me. Okay, now you don't know. Okay, if you have some question, just click on the participant and raise your hand. Then I will unmute you. Okay, if you cannot hear me, raise your hand. All right, so this is this example. And let's see the, okay, so the next slide is oxidizing reducing agent. Okay. So as I said, so the modern table has this reduction potentials. So what that means is the more positive value of this E naught reduction, the greater the tendency for the reduction under standard condition. So this part here is part of the table, and we have the numbers. So again, all those reactions here, all those equations here written are reduction reactions. And we can see those more positive number on the top. And then you can see there are a few specifications we can see about those reactions. So those, what I can see is the most positive value of E reduction on the top, most negative value of the E reduction not at the bottom. Then you can see those on the left side, which means those rectangles. So they are, when I think about they are oxidants and then goes up. So they are strength of oxidant increases because they have a very large potential want to be reduced. That means they grab electron very strongly. So then on this side, we'll see the reduction potentials. So the strength of reducing agent increases from top to bottom. So those species at the bottom of this right side of the equation, so usually will be some of those solid metals. They are very good reducing agent because they can donate electron very easy. Okay, so therefore, if this from this graph here, we can see compare this few substance, molecule, or ions. We can see this F2 gas is the strongest oxidant, and the lithium solid, Li solid, is the strongest reducing agent. Okay, so this is how we can compare who is a stronger oxidant and who is a stronger reductant. Yeah, so then we will do this practice. So based on the table in the last table you just saw, which of the following species will you expect to be the strongest oxidizing agent? And we can see we have a few, we have 5 species given. The first one, chloride aqueous. The second one, chlorine gas. Number 3 is oxygen gas. Then we have a hydrogen ion, then sodium ion. So if you go back to the table 20.1, we can see there are a few half reactions. We can see this chlorine here. So chlorine here. So that's chlorine, then chloride. So most likely chloride cannot be an oxidant because it's already reduced. So to be an oxidant, you want to be reduced even more. So very unlikely. So this Cl magnetic ion will receive another electron to be reduced furthermore. So that not happen. So we'll probably just, so the question have this choice, but that is really out of the question, not our choice. So we can see we have Cl2 gas. Yeah, so what I see is very general. If in the question give you some of those species ions, which is on this side of the arrow, so in that example, you have the chloride ion. So you can see that ion most likely will not be your oxidant if you want to choose the stronger oxidizing agent. So we have 5 choices. The first choice is Cl1 negative. So Cl1 negative on the right side. So that's not our answer. Then we have a few other. We have chlorine gas, oxygen gas, and then we have H plus ion. We have a sodium ion. So we have 5 choices. So chlorine gas, you can see easy. So here, the chlorine gas have very large reduction potential. Means chlorine gas is a very good, a very strong oxidizer. So number is 1.36. And then you can see oxygen gas kind of confusing. There are quite a few equations have the O2. So this equation, for example, O2 plus H plus become water. And the last one at the bottom here, so O2 plus 2H plus 2 electron produce hydrogen peroxide. So that's another equation. You go to the next table, so there are 1 more equation. So this equation, so oxygen gas plus water plus electron produce hydroxide. So which one you choose? You want to compare that fairly. You want to choose, see here, chlorine gas just plus 2 electron without any other help. So you don't want to choose this one because this one kind of tells us what is the oxidation strength of O2 gas in like acidic solution. So the kind of your acid is very concentrated. Then if you actually become less concentrated, you have this reduction potential for this O2 gas. So we'll choose this reaction equation for the O2 gas because this is kind of neutral. So therefore, it's comparable to the chlorine because chlorine, as I said in the last table, without any other help. And once we know that, then you can see this H plus is standard, so H plus here, and then sodium is here, so that we have weaker and weaker oxidant. So therefore, if we go back to this, and we can see our strongest strongest oxidizing agent will be that. So if you want to summarize with those numbers, you probably can just see, you can get the number from the table. Let's make a list. And then we have these few reactions. So our first reaction is Cl2 gas. And we see plus 2 electrons, produce 2 Cl aqueous. So that has a number positive 1.36, all those in watts. So we have a 3 reaction has oxygen gas involved. So the first one is in a more concentrated acidic solution. So written as this, then you produce a 2H2O liquid. Yeah, so that is relatively strong. In this way, oxygen is very strong oxidizer, so plus 1.26. So even that is not comparable to chlorine gas. So chlorine gas is 1.36. So O2 gas can also act as oxidizer, but in a less concentrated acid solution. So you have only 2H plus, then plus 2 electrons. So what's the product is not H2O, is H2O2, which means hydrogen peroxide. So the state becomes aqueous. Or you can take O2 gas, don't use any acid, just use water. So water is liquid, then plus 4 electrons to produce hydroxide. So this has number plus 0.68 plus 0.40. So all these three is for oxygen gas. And then we prefer to choose the last one. So two more choice is 8 plus. So 8 plus aqueous, and we have to use 2 of that to balance the equation. So plus 2 electrons produce H2 gas. By definition, so that's 0. So then last one, you have sodium ion plus 1 electron produce Na solid. And then that's mathematical number, 2.71. Okay, so therefore, so this has largest E0 reduction. That means our strongest oxidant. Therefore, our choice will be B. Okay, any question? If you have a question, you can raise your hand by go to participant and click on raise your hand. Okay, so next we are going to learn how to relating the E cell to the free energy change. In last chapter, we learned that delta G, free Gibbs energy change. So Gibbs is a chemist long time ago in University of Johns Hopkins in Baltimore. So so then we see for a spontaneous redox reaction, we will have a positive cell potential or positive E0 cell. And the way to calculate E0 cell is by using this equation. So this is true for all the reduction reactions, and not only for the voltaic cell. Then we know the Gibbs free energy change is also a measure of spontaneity from last chapter. So we know for a spontaneous chemical reaction, so delta G is negative or delta G less than 0. So clearly there are some connections between the delta G and the E cell, right? Because they both can tell the spontaneity of a process. So therefore there must be a connection. And how do they relate it? So the equation to relating the delta G and E cell is using this equation. So this is the relationship between the Gibbs free energy change and the cell potential. So then what are those variables in this equation? We have 4 variables. We know delta G is the Gibbs free energy change, E cell is the cell potential. What is F? Well, F is the Faraday constant. So the number 9645 coulomb per mole. So for every 1 mole of electron, so how many charge of 1 mole electron has? So Faraday constant tells us that. So for every 1 mole electron has 96485 coulomb. So what is N? Well, N is the number of electrons involved in the reduction reaction in the overall reaction, or you can say should be balanced overall equation with simplest coefficient. So once you have the overall equation balance, you should have the simplest coefficient. You don't have like everyone has 2, 2, 2. So you want to have the simplest coefficient. Then you can examine that equation, how many electrons are transferred between the reduction reaction and the oxidation reaction. Okay, so then this equation actually, all you need to memorize between these 3 quantities. So we know we have the free energy can tell us spontaneity. And then we also know that E cell can tell us spontaneity. From chapter 14, 15, 16, we also know this K. What is the K? So K is our equilibrium constant. It can tell you the spontaneity by compare Q with K. So if your Q smaller than K, your reaction going forward is spontaneous. So all the 3 are negative. So because they all can tell your direction of your process or your chemical reaction. So therefore, this equation summarizes all the equation you need between these 3 something. Or you can use this diagram. Okay, so in this diagram, you see there are 3 equations. So this first equation comes from the first equal sign here. Okay, So this second equation comes from the second equal sign. So from that, we can see delta G equals this, also equals this. So therefore, clearly you can see delta G 0 equals negative RT L and K. Therefore, we have this equation. Okay. Now the last equation comes from, you will take negative and FE 0. You want to give that more name called cell equals negative RT L and K. Okay. So this comes from that, and then we can see that from this equation, we can see that take this last two parts to get this equation. So rearrange this equation, you have negative, negative comes out, then you divide the NF out, or you can simply divide the negative NF, divide negative NF. That's how you get this equation. So depending on what you like, you can memorize this diagram or memorize this equation on the top. Right. So this next problem is you want to use in that new equations and to calculate a few things. So use the standard reduction planter in the table to calculate the standard free energy change delta H and the equilibrium constant K at 298 Kelvin for this reaction. And the second part is if we write this equation in the other way, we mean pretty much take that equation divided by 2. And then what will be the new E delta G and K for this one? So what do we see? We will just see to solve the first part of the question, part A, we will use the data in table 20.1 and equation 20.10 to see what is our EZ. This equation just means you have the E cell equals E reduct on the cathode minus E red on the anode. All right. So then use E and that to calculating delta G. So that equation pretty much just delta G equals negative NF E cell. Then lastly, you want to use that equation. So what's that equation? I don't think you or forget. So here are those equations. You can either, I don't remember the number, you can either use in this one or that one. As we're using so delta G naught equals RT Ln K. It is Ln. All right. So to do that, so obviously we have to first calculate what is our E cell. We have to know what is our equations. So I'll copy this overall equation on the top. So therefore, you can identify from this equation what is happening on the anode. So on the anode will be the oxidation. So you can see this Ag solid here become Ag plus ion. So Ag or the silver lost electrons. Therefore, the half reaction will be the 4 Ag solid produce 4 Ag plus ion plus 4 electrons. So the remaining part will be the O2 gas plus 4 H plus aqueous plus 4 electron produce 2 H2 liquid. So that will be the reduction reaction. So once you identify your reduction reaction, oxidation reaction, as we know, reduction reaction will happen on the at our cathode. So this is our happen on the anode. Then you see the formula. So the formula will be E cell equals E reduction, just this is the name, the reduction potential, happened on the cathode minus E reduction happened on the anode. So if everything at a standard, then you have standard, standard, standard. Okay, so therefore we plug those numbers, plug this number here for the cathode, plug this number on the anode. We have this equation, the subtracting, get 0.43 volts. So we solve one part of the problem. So we say this equals, therefore the cell, we rewrite the E naught in standard for the cell. Okay, so once we know E cell, we're using this equation to get our delta G. So delta G equals negative NF. So then how do you find out what is N? So N equals electrons transferred in the overall equation, balanced overall equation with Siemens ratio. So this is the balanced equation over Siemens ratio, and or that equation comes from adding these two equations, therefore there are 4 electrons. So usually if you see the electron number in the 2 half reaction are the same, and you just take the same number. If one reaction give you, let's say, 5 electrons, the other one give you 2 electrons, then what do you use? Well, you have to find out, when you balance the equation, you will take this 5 times 2 and 2 times 5, so therefore you get 10. And so you get this number. So those numbers become kind of a gigantic big. So be very careful. If you rounding the number too early, you will get quite a different number. So therefore, I keep this number, but the test will say we have to run into 2 sig figs, they're 1.7, and then next you use this number to calculate the K. So we know our K to be a very large number, and because our delta G is our delta G is a very large negative number. Okay, so the equation you have different equations you can use to calculating this K. So this is one they use in the textbook, and you can obviously use the other one. So the other one you can use. So the choice is what we say is E cell equals RT and NF, L, and K. Okay, so therefore we are using this one. So here we use this. So therefore we find out delta G from the last question. We plug in here, and then I will plug the R. So R, so this R, this part is R. So then this is T. All right. So therefore we see the cancellation of the unit, and then we see L and K equal to 69. So therefore K will equals E to the positive 69. So E is exponential function. So that's expected. So this K is a gigantic number, 10 to the positive 29. So in the practice questions, depending on how you run the numbers, so you will get this 10 to the 29 pretty much right. And this number, depending on how we run them, you might get quite a few different numbers. So this can vary